In today's problem, we're going to talk about a particle that is in an infinite potential well. This problem is mainly characterized by having essentially a particle in the system where it's bounded between 2 points. At these 2 points, you have essentially sharp peaks in potential, which are effectively infinite. In reality, of course, you wouldn't have this sort of infinite potential, but this problem is a fair approximation for when the potential is much greater than the energy. Essentially, V much greater than E over here. So to draw a graph of this, potential versus X, or potential versus position, X just being a position variable. So as in my problem, I do it at 0 and A, where I have these infinite potential peaks. So you can see that this sort of forms a well shape, which is where the name is derived from. So the particle is essentially existing in its region between 0 and A. And farther out, you have the wave function set to 0 on both sides. That's essentially what will also make up our boundary conditions. Alright, so now we invoke the Schrodinger equation, because this is a problem in quantum mechanics, and you can solve it with this equation. So the Schrodinger equation is H psi equals E psi, H being the Hamiltonian, A psi being the wave function, and E is the energy eigenvalue. Now this problem is a time independent one, or at least in this case it is, and also non-relativistic. So the Hamiltonian first takes on the form p squared over 2m plus v. Now p is the momentum, m is the mass of the particle in this case, and v is the potential. Now between this region, between 0 and a, in this region, we have v equals 0. And wave function is essentially what we're trying to solve for, as well as the energy of the particle. Alright, so the momentum, recall that the operator is equal to negative I h bar del, and I is the imaginary unit in this case, and the del operator is the gradient, which only in one dimension is derivative with respect to x. Now squared, this becomes negative h bar squared d squared over d squared x. Alright, so now we write our Schrodinger equation by plugging this value in. Essentially we have this. Now v equals 0, so this term gets cancelled out, so then all we're left with is essentially this kinetic energy portion. So plugging in what p squared is, we have d squared psi. Alright, so this is actually a problem that's usually encountered early on in most quantum mechanics courses. At least in mine it was. So I suppose you have to get used to the formalism of when multiplying, or what would look like multiplying values together, like p squared and psi. It's more like one is acting on the other. You have to get used to the idea of operators. So like p, the p squared operator is acting on psi. As you can explicitly see, it's by itself it's only a double derivative with respect to x in this case. So then that is taken on psi, acting on it. So what we have here is a second order linear or ordinary differential equation, essentially, which we could solve for. So now I move this term over to the other side. So we have 2me over h bar squared sine negative. Now, bring this all over to one side. So we have 0 on one side of the equals sign. Alright. So essentially we have a wave function that has to take on a form that when we take a double derivative of it, you get essentially a constant that's popping out, or at least here you can, especially in this one, you could see this relation. You get a constant, this term being a constant, times its original, times the original wave function. So two types of solutions come to mind, and that would be the exponential as well as trigonometric. Alright, so we take on, we argue that psi can take on the form ae to the rx, a being the natural number, being raised to r, which is the root we want to find, and a is just a constant, arbitrary constant. Alright, so d squared psi then would be r squared ae to the rx, because this r comes down through chain rule afterwards, so you get the original times r squared basically. Alright, so plugging this in, we have r squared ae to rx plus, okay, so now I'm gonna denote this as c, so then I can make this easier. So then we have it like that. Now I factor out ae to the rx, and we're left with r squared plus c equals 0. Now, so to solve for this, one trivial solution would be that a equals 0, but that doesn't give us any information. The exponential term on the outside can never equal 0, or I suppose you could argue that when the limit as x approaches negative infinity, then it would equal 0, but that's not realistic. So we look at this term in the bracket, and we set that to 0. So bringing c over to the other side, and then taking the square root of both sides, we have r equals plus minus square root negative c. Now I take out this negative being square rooted into outside the bracket, and our friend, the imaginary unit I, comes out. So we have plus minus I. I'll just write this down on the side just so you remember. I is the square root of negative 1. So we have plus minus I square root c. Whoa, sorry. Alright. Okay, so now we have essentially two roots. So our wave function will have to have two constants. So we'll denote the first one by a, just it's arbitrary. So our first root is I square root c, then x, plus b, just another constant, to negative I square root c, x. So this is so far our general form of the wave function. Now this can actually be rewritten, and it is much more convenient to do so, into trigonometric form. So I could write it like this. Instead. Now these two are equivalent, so it arises through the Euler identity, which you can enforce in this situation. You can see that e to the I square root cx is the cos square root cx plus I sine square root cx, and then the I becomes absorbed into the a and b, and you collect those together and you get c and d basically. I could exploit that in another video maybe, but for the sake of time, I'm going to just argue that these are equivalent because they are. Alright, so moving on. Now we have to enforce our boundary conditions. So it's almost like a process of elimination where we're sort of slowly, or not slowly, we're just getting closer to trying to find the true form of our wave function, you could say. So the first boundary condition, recall at the beginning of this video I said that psi should equal 0 outside the region that's allowed. So it's none 0 at 0 to A, I guess you'd say, and 0 everywhere else. This is obviously due to the potential just sort of forcing the wave function to collapse to 0 at those points. So the first boundary condition, psi equals 0 at x equals 0. Alright, let's enforce that. So we get c cos of 0 plus d sine of 0, because we plugged in x equals 0 for both. Sine of 0 is 0. Cos of 0 is equal to 1. So essentially we get c equals 0. Well, that eliminates the entire cos term then. So therefore, our wave function reduces to d sine square root c x. Now we enforce boundary condition number 2. The other point was at A. A is just this arbitrary point, just for the sake of the problem. So psi equals 0 at x equals A. Alright, so again, force that. So we get square root c A. Sorry, cos is already out. So we got d sine square root c A. Alright, so one solution to this would be if d was 0, but that just reduces psi, the wave function, to 0, so that doesn't give us any information. So the other part is, when does sine of something give us 0? Well, if you recall sine, the function sine of x, let's say, just for some value x, sinusoidal nature. Alright, so here we have, starts at 0, goes in a wave, comes back at pi to 0, then at 2 pi, 3 pi. So you can see a pattern rising here. Every time the quantity in the bracket is essentially equal to n pi is when sine reduces to 0. So we argue that. We say the quantity in the bracket, in this case Ca, has to equal n pi. N is integer value. We say it's from n equals 1, 2, 3, dot, dot, dot. Alright. So now recall what C was. That was 2me over h bar squared. And now I just use some algebra to rearrange this so then I have it in terms of E. Okay, so bringing A over to the other side puts it on the bottom, and then squaring both sides, we have n squared pi squared over a squared. Then this gives us, bringing 2m over to the side puts it on bottom, h bar squared comes to the top. So essentially we have n squared pi squared h bar squared over 2ma squared. And this is our energy of the particle in this system. And more specifically, for the n equals 1 case, we have 0 point energy, lowest possible energy state possible for this particle. Just plug that in, we have 2ma squared. So this also reveals to us the quantization nature, since only discrete values of the energy are allowed. And I guess that this sort of arises through the boundary condition itself, examining that the quantity in the bracket can only equal a sort of integer of pi, I suppose, then correlates, or eventually you can see down the line that energy then consequently is also quantized because of that relation. All right.